Okay, this will be some examples from section 3.5 where we're dealing with exponential functions and logarithmic function equations. Um, a lot of it's just formula based and calculator work. I'm going to take the liberty of perhaps leaving some of these answers values rather than rounded values, even these money ones, um, and leave the calculator work up to the viewer. So here on number 15, we're to find the time it takes for P dollars. So they don't tell me how many dollars we start with to triple if the interest rate is compounded at 6% continuously. So if it's continuous compounding, I'm going to use my amount equals my principal, what I started with, e to the r times t. And I am starting with p, but in this case, if it's going to triple, then the amount I'm going to end up with is 3p equals p e to the r. Oop, that's bad. Not times r, but to the rt. And if I know the rate is 6%, then I can change this to 0.06 times t. My problem is I have two variables. However, when I divide by p, I get 3 equals e to the 0.06 t. And so now, and the reason I did that is because when we have an exponent that, that is a variable, we want to isolate as best we can the exponential factor term. Okay, so in this case, once that happens, I can take the log of both sides, but it would be crazy since we're in base e not to use log base e or ln. So I get ln3 equals 0.06t ln e. But this is the exponent that turns e into e. This is just 1. If that was ln7, then I would have to divide both sides by ln7. But in this case, I get t equals ln3 divided by 0.06. And that is the time it would take. Now, I do want to suggest a very common error from this step is to say, okay, divide by 0.06 and get ln of 3 on 0.06 equals t. That, no good. We're not dividing 3 by 0.06. We're dividing ln of 3 post function by 0.06. And from that, again, I'll leave finding the time up to the viewer. Number 19, find the amount of an isotope that remains after 1,000 years if its half-life is 1599 and the initial quantity is known to have been 10 grams. Our half-life formula, this is one that should make sense to you. If it doesn't, you may want to ask questions on that. I would write it the amount we have after time t is passed equals the initial amount. And with a half-life, what do? We just start multiplying by half. How often do we multiply by a half? In this case, every 1599 or every 1,599 years. So after 1,000 years, I haven't multiplied by a half yet. I've multiplied by a fraction, 1,000 out of 1599, that fraction. So it is the amount of time over the actual half-life. So what we have here is our amount after 1,000 equals our initial amount 10 times 1/2 to the time 1,000 on 1599. And that I would leave to the viewer. Although I will warn you here again of a common mistake. A common mistake here is to bring that 5 in and make that 5 to the 1,000 on 1599, and that is bad because, please excuse my dear Aunt Sally, we handle parentheses first. Then we handle exponents. And then we're going to multiply. So very, very common, but unforgivable mistake there because we need to know order of operations. We're going to take care of this exponent before we introduce that 10. So just the rest up to you with your calculator. Find the exponential model, y equals. This is not so different than amount equals p e to the rt. It's really kind of the same formula. And what we learned is that P is our starting amount, or in other words, at this point, excuse me, that's not 1, 0. At this point, 0, 1, right here, when X is 0, I get Y, or I get 1 for Y equals A e to the B times 0 for X. Or that is 1 equals A, and e to the 0th is 1. So A is 1. So far I know my formula is Y equals 1 e to the something times X. I just need to find B. But I have another point to work with here, 3, 10. So now I'm going to put those values in to this formula, and I get Y is 10 when X is 3. I just need to figure out what B is. X is 3, B. That's really not very pretty. Let's try that again. When X is 3, we get 10 equals 1 times e to the 3b, or ln 10 equals ln e to the 3b, but this is the exponent that turns e into e to the 3b, so ln 10 is just 3b, and b is ln 10 on 3, all of it on 3. So my model is y equals e to the ln 10 on 3 times x. Now, certainly in the back of the book, this would be represented as a decimal. That is the exact value of the model, and I would leave ln 10 on 3 up to the viewer with a calculator. I think I skipped one here. Let's try that again. I did skip one. Okay, this is virtually the exact same problem. Find the exponential model, same thing, a graph that passes through 0, 1, and 1, 2, 3, 4, 5, 1. So we got a point here, we got a point here, we got a graph, maybe I'll make that green, and we got a graph that looks like this. It has a horizontal asymptote when y equals 0. So we look something like this, exponential. Same exact problem. This is key. We get this point 0, 1, which means y is 1 when x is 0. And the nice thing about that is that absorbs the b, e to the 0th 1, so a is 1. And we're starting to learn, oh, that's just our initial amount. Same as with y equals p e to the rt. Our initial amount is our principal. So now, substituting 1 for a and looking at our next point, 5, 1, I can say y, is that truly 5, 1? I think this is a mistake. I'm going to back this up because that is not exponential. I'm going to say that this is 1, 5, and back this guy up. Apologize for that, but there is no way that could be it because that was just flatlined. So let's go ahead with 1, 5 on this. So 0, 1, 1, 5, and we've got a line that looks like that guy. So if that's the case, now I've got an equation where 5, 1, y is 5 when a is 1, and x is, well, I'm really tempted to start this over. If I wasn't running short on time, I would. Here we're 1, 5. So y is 5 when x is 1. So now we get 5 is e to the b, or ln 5 is ln e to the b, or b is ln 5. So finally, after botching that up a few times, we end up with y equals a1 e to the b ln 5 times x, or x ln 5. Okay, apologies there. I'm certain that must be 1.5 in the book, but I am away from the book right now. Okay, another one. Same thing. The population in Australia in 2000. I'm going to put 2000 at like times 0. It was 19.2 million. And then 2010, so at time 10 years, we jumped up to 20.9 million. So our growth exponential along those lines. I know I've exaggerated that distance between those two. Find the exponential growth model and predict the population for 2030. So same exact thing. Our initial amount is 19.2 million. So our y equals our initial amount, 19.2 times e to the bx if we use the previous one. Some people use k for that pretty frequently. But now I've got another ordered pair here. I'll get it right this time. 10, 20.9 million. And I can say y is 20.9 when x is 10. Or e to the 10b equals 20.9 divided by 19.2 ln. And I get 10b is ln 20.9 on 19.2, if you like. Divide by 10, and that's b. That's the exact value of b. We would probably now want to round that. I'm going to say this thing rounds to star. And so now to find what we would have in 2030, that is 30 years after we start. So our amount after 30 years would equal our initial amount times e to the b, which is this, and rounded to star, times x. The x in that case would be 30. So substituting this value in here for star, this is straight calculator. Okay, the half-life of a radioactive radium is 1599 years. What percent is present? What percent is present of what percent of a present amount of radioactive radium will remain after 100 years? Well, most of it will, but we don't know how much we start with. You could start with 1 gram and figure out how many we left. You could start with 1 ton and figure out how much we have left. I'm just going to start with 100 units because we're dealing in percents and say, wonder what we end up with. So what do we do with half-lives? We multiply by a half. How many times are we going to multiply by a half? Not many, just a fraction of that. And in this case, the answer I would get, since I started with 100, if I end up with 97 or something, is an actual percentage. We don't need to move the decimal. So not a bad way to approach that percent problem. Okay, Richter scale. This is kind of weird to me. The Richter scale, where the initial intensity is always measured at 1, that's our I naught. The initial intensity is I naught. So this thing is really just log base 10 of the intensity. Find the intensity of the following earthquakes. So they just give me the values. They tell me R is 6.1, so that is 6.1 equals log base 10 of I. But definition of log says this thing, which is 6.1, so 6.1 is the exponent that turns 10 into I, 10 to the 6.1. Pretty big, because 10 to the 6th is a 10 with 5 more zeros added onto it. So this thing is greater than, and you can go to calculator, but this thing is greater than 1,000,000 on the Richter scale. Well, I'm going to skip B. How about C? Now we go 9 equals, and 9, oh, 9's just a little bit more than 6. Can't be too much worse. Well, let's see. That's log. Try this again. Nervous. I hope this continues to record. Hopefully this works because I just got unplugged. Log base 10 of I, and I get 10 to the ninth equals I. Well, that is a 10 with 8 more zeros. And we see this is 9 is quite a bit more extensive damage than 6.1. If you've ever studied earthquakes at all, you realize that 9 is a bad, bad deal. 6 is no fun, but 9 is total devastation. Okay, other than the mistakes, hope that works for you. Appreciate you checking in on this, and make certain you're bringing up questions if you have them.